have sampling in vertical profiles. We can get surface underway measurements. There's a lot of different ways that we can incorporate the different measurements in the measurement table. So for every single one in these columns of the measurement table I've highlighted here at the right, we've also prioritized every measurement by the sampling mode and platform so that we can see whether certain measurements are useful or required in certain instances. Okay. So the next thing we wanted to do was come up with a notional cruise plan for the implementation of these observations. So we can take all of these observations that are prioritized for the process ship or for the survey ship and block out in 2-hour increments all of those, everything that's required to characterize a single ecosystem in carbon cycling state. We can carry those out in about 8 days. 8 days is also sort of the time limit that we've set for, time scale we set rather for an ecosystem in carbon cycling state. If we're thinking about time scales, for instance, for particles from the surface ocean to sink down to hundreds of meters deep. So if we take those 8-day ecosystem and carbon cycling state estimates, we can get 3 of those in on a single 27-day cruise if we include some weather days and required ship operations. So the nominal cruise plan or notional cruise plan maps the sampling activities onto the ship and also considers measurement interdependency. So if we have things that need to happen together on the same ship, then that's also accounted for in how these activities have been planned for this notional cruise plan. There's lots more detail here also in the exports implementation plan. So I just showed you a couple of timelines for a notional cruise schedule. We can back out. So now we're looking at a notional plan for the autonomous observing system, so including floats and gliders. And again, the idea here is that these platforms give us continuous capabilities and persistence across the regional scale where we're sampling a whole year around our cruises. So here we've got our ships out doing the ship-based measurements, and then we've got floats and gliders that are cross-calibrated during the cruises and with one another, and now enabling us to get that entire year cycle there. Finally, backing out to another timeline, this one is 7 years long. This is the suggested timeline for the implementation of the goal plan. You can see we are here in the middle of 2016. The science definition team's work is ongoing, but will wrap up in the fall. We already have, in Rose's 2015, there was a call for data mining and modeling work that will sort of lay the ground, sort of trying to get additional ecosystem and carbon cycling states from existing data sets, so that will get underway. If everything goes according to the suggested timeline, we would have the Exports Project Office, which would work for the duration of the project starting in mid-2017. And what we've done here in this planning suggestion is to break apart the work that relies on observations in the field and projects that are taking field observations. We've broken those out into what we're calling phase 1, so work that's required to answer science questions 1 and 2, and then phase 2, the modeling and synthesis work that will answer science question 3. So phase 1 would start notionally in 2018 and go for 5 years, and phase 2 in 2022 and go for 3 years, overlapping with PACE operations. And then we have our 2 cruise years here, 1 in each basin. We're suggesting a management structure that would consist of a lead and a deputy lead scientist, as well as representatives from each of the funded PI groups in different research areas that are part of exports to form the science steering committee that would help manage field operations and coordinate data management, things like that. And we're suggesting there be staggered turnover among these leadership team members, so we always have some prior experience and new voices coming in throughout. Okay, so that's an overview of the implementation plan. Like I said, I really just sort of hit the major points. There's a lot of detail that's also available on the web. The science definition team was, in addition to being charged with coming up with a detailed suggested implementation plan, we were also charged with coming up with a robust cost estimate for that. So we made this cost estimate for the goal plan, which again was the plan that we think we have the highest confidence that it will enable us to actually answer the 3 export science questions. So the goal plan, we were able to cost that by just adding up all of the pieces. And it comes down to $71.5 million over 7 years. This pie chart shows the breakdown of the project costs. You can see that almost half of that goes into projects. So these would be individual PI groups. So this would be people carrying out the observational and modeling work, part of it in phase 1 and part in phase 2. The next biggest chunk is ship time and autonomous sampling devices and operational costs. There's smaller costs associated with hydrographic sampling, so standard analyses like nutrients that would be done as part of a centrally managed team, data management, project office. NASA holds about 10% of field costs in reserve as contingency, and then logistics. I just want to further break down a little bit the biggest pie slices here. PI projects in the goal plan, we're looking at 23 projects in phase 1. So that would be 20 necessary to address all of those program elements in the measurement table, and then 3 that are marked for things that aren't in the measurement table, but innovative ways that people come up with to answer the science questions that are not in the measurement table. And then there are 8 projects that are budgeted for phase 2 for the synthesis and modeling work. The next biggest chunk is ship time. We're talking about 338 ship days to carry out two ship cruises in each of 2 oceans. And then finally, there's the autonomous sampling operation, which pretty much scales with the number of cruises. If we're trying to get persistence of sampling around each of our cruises, that autonomous fleet is going to scale with that. Okay. So the final thing that I want to talk through briefly at the end of my talk here are how can we evaluate alternatives to the goal plan? Because there's uncertainty in agency budgets, and the community is going to propose ways that they think are the best way to carry out this work. So if we're weighing these different options for implementation, what are the trade-offs between cost and science return, particularly to fit different budget scenarios? So what I'm showing you here is a table that's taken straight from the science plan. I'm going to go through it rather quickly, but you can go look at it on your own. The table shows 7 different implementation options that the science definition team considered. The top line is the goal plan that I've just spent a bunch of time talking to you guys about the details of. Goal light is the same as the goal plan, only we take out those 3 projects that are not in the measurement table explicitly. The remaining options scale effort down in a number of different ways. The first is decreasing the number of cruises or the number of basins that exports makes observations in. So for plans C, D, E, F, and G, we're going down the number of cruises and the number of basins. We also evaluated implementation options that involve going out with just 1 ship instead of 2. So instead of having 1 ship that's water parcel following and 1 ship that's doing geographically distributed survey work, instead we would only have the 1 ship. And we also evaluated options that dropped support for phase 2 projects. So assuming if we can get this coordinated, incredibly detailed set of observations in the field, then those data will be there and synthesis will happen, but not explicitly as part of exports. So things below the line here, options E, F, and G, don't have any phase 2 projects. So there's quite a difference in cost scale here as well. So that's just adjusting total effort, people that are involved, ship time that's necessary. So we wanted to think about ways of evaluating these different options in terms of the science return and the risk to the science goals of export. So the science definition team came up with this, what we're calling a trade space. I think maybe engineers call it that too, I don't know. But we're basically going to plot our different implementation options on this scale here. On the y-axis, it's labeled likelihood of observing all export pathways. So this is the probability that by going out and carrying out this particular implementation option, we're actually going to be able to fully constrain pathways 1 through 5 on your CFAT cards. On the x-axis, on the horizontal axis here, we're looking at the range of ecosystem and carbon cycling states that are observed. So are we going to be able to fully get a large dynamic range in the way that the biological pump is operating among our different observations? There's some reference lines on this trade space as well. Current state of the art, the blue line here, determine all export pathways, orange line here, and global applicability here. So the highest science return, the least risky science, where we're most likely to be answering our questions, is going to be in the upper right-hand corner of the plot where the color is darker. And that's where our goal plan plots out. So it's minimizing the risk that we wouldn't answer all of our science questions by making sure we're observing all the export pathways and fully constraining them, and then by making measurements that span 12 ecosystem and carbon cycling states. And it includes those innovation projects and phase 2 to answer science question 3. Just as an example, I've also plotted our implementation option D on here. So this is one that goes to 3 cruises in 1 basin instead of 2 cruises in 2 basins. So we've decreased, by doing that, the range of ecosystem and carbon cycling states that are observed would decrease because we'd just be making observations in 1 ocean instead of 2. And it's also taken out those innovation projects. So it's going to increase the risks a little bit for science question 3 because we're not going to be getting as broad of a range of ecosystem and carbon cycling states to build those prognostic models. And then again, as a comparison, I've put implementation option F up here. So this is one where we're now going down to 1 ship, 2 cruises in 1 basin. And by only having 1 ship, we're not going to be able to make that depth of measurements that we could make with 2. For instance, it's likely we would not be able to constrain pathway 4, that submesoscale subduction pathway. But even, here's all the others as well. Even those options that are on using 1 ship, for instance, and not fully constraining everything, are still state of the art. They would still be some of the most comprehensive measurements that we've made of the ocean biological pump. So no matter what implementation option happens, we're going to be breaking new ground with exports, which is exciting. So some challenges going forward. We need to strike a balance between discovery and innovation and broad participation, agency, mission, and cost. We need to find ways of supporting coordination among the competed projects to ensure a complete measurement set. So one of the things about exports is that it is very collaborative and really broad interlocking sets of measurements. We need to develop effective partnerships with international entities and other funding agencies in order to bring some of this to fruition. And we want to make sure that phase 2 occurs so that we have that synthesis and this ability to go forward with new capabilities for satellite algorithms once PACE is launched. So with that, I want to thank you for your attention. We're going to transition right into the Q&A and panel part of this session. Before I do that, I just want everybody from the science definition team to stand up and wave. There's a whole bunch of us in the room, and yeah. And everyone that's here that's on the team will sort of serve as an extended panel a little bit as we take questions about this program. So next steps and things to think about as we go into discussion here is that exports doesn't exist yet, and it's not going to exist unless the community expresses engagement, enthusiasm, and support for the science, for the science question that's so important here and to your agency leaders. If exports moves forward, the community that's in this room is who's going to carry it out, and so there's so many opportunities here. And importantly, we want the implementation plan, which is just a draft right now, to reflect your ideas. So any feedback that you can give, either here or later on in emails, would be really appreciated. That's what we're looking for at this point, is to sort of hand this out to the community and get it moving forward. Okay, so with that, if I could get the other speakers from the talks earlier today up front, we're going to go into panel mode.